Noah Stephens-Davidowitz. Oh, yeah, talk is recorded. Yeah, I'm glad to introduce you Noah Stephens-Davidowitz, who was a postdoc at MIT and did his PhD with Oded Regev and is soon to be assistant professor at Cornell University. He's going to introduce us to Lattice algorithm. So Noah, it's up to you.
Okay, great. So the goal of this talk is to give you sort of a very high level sort of crash course survey, whatever you want to call it, of lattice algorithms. There are going to be other talks about lattices in both the Asia Pacific and the European Summer School. I think Yuntao will be talking about it in 2 days in the Asia Pacific, and then also Philippe and Ilya in the European, so they'll go into more detail. Also, if you're interested in any of this stuff, we just recently had a whole semester on lattices at Simons, and they're like wonderful videos online. So if you Google like lattices Simons Institute, you'll find a lot more detail. So my goal here is to give you sort of a high level picture. Oh, and I forgot to say, thank you for inviting me. And also, I hope everyone's doing well. I know these are trying times. But yeah, let's talk about lattices.
Just one thing for the organization. So we mute, as you can see, we muted everyone. So if you want to ask questions during the talk, just use the global chat. And it's okay to interrupt you during your talk if people are curious. Okay, so yeah. Just post your question in the global chat, and we will unmute you when needed. So that like everyone is not talking at the same time. So yeah,
sounds good. Yeah, the more interruptions, the better, because otherwise I'll get bored.
Of course. So no, it's up to you now.
Okay, great. So yeah, let's talk about lattices. So I should tell you what these things are. So a lattice, which I'll always write in this like curly red L thing, it's a discrete set of vectors in n-dimensional space. So here's a 2-dimensional lattice, and the lattice itself is specified. So like as like a computational object, we write a lattice by specifying some basis elements, B1 through Bn. These are linearly independent vectors in n-dimensional space. So here's a basis for this lattice. And the lattice itself is then the set of integer linear combinations of the basis vectors. So for example, I left out the example, but you can see how this gives this nice sort of periodic set. Like I can keep adding either B1 or B2 to my lattice vectors and keep going. So you get this nice, beautiful, discrete periodic set. And sort of important geometric quantity is what we call lambda1. It's maybe not the best notation, but lambda1 is the length of the shortest non-zero vector in the lattice. So on this lattice, this black line that I've drawn represents lambda1, assuming that I eyeballed this correctly. So yeah, you notice that you have to say it's the length of the minimal non-zero vector in the lattice. This is kind of a huge pain, right? So the shortest vector in the lattice is the 0 vector, but we want the shortest non-zero vector. And you'll see that, well, actually you'll see a while from now, sort of in the second half of the talk, that the fact that you want a non-zero vector is always rather annoying algorithmically. But yeah, that's far in the future. So the computational problem that we're most interested in is the shortest vector problem, which I'll call SVP. And it's defined as follows. So SVP takes as input a lattice specified by a basis. And the goal is to find the shortest non-zero vector in the lattice. So for example, this would be a solution to SVP on this lattice, again, assuming I eyeballed it correctly. So we often sort of don't care about the exact problem. We're happy with approximations. So gamma SVP is the variant of the problem where instead of needing an absolute shortest vector, we're okay with being off by a factor of gamma. So like this vector up higher would be maybe a 3 approximation or a 2 approximation or something to the shortest vector. Oh, I figured out how I can see myself. This is nice. Okay. So first of all, this problem, I think it should hopefully be clear that it's in NP. And it's actually NP complete. So it's in NP because like I can give a witness a short as a witness a short vector, and it's NP hard. It's even NP hard to approximate, although this is only known for actually gamma equal to a constant. The specific details are sort of difficult to understand at first. It turns out, and this is not obvious at all, that this problem is interesting for a gigantic range of approximation factors gamma. So it's interesting as an exact problem for gamma equals 1. It's also interesting for gamma equals 2 to the n, which is not obvious at all when you first see this problem. And for crypto, it turns out, again, this is not obvious, that polynomial approximation factors are what's relevant. So if you want to break crypto, you have to solve SVP or variance of SVP up to a polynomial approximation factor. And I'll give you a small amount of intuition for why this is true, but not really. So this is a really, really well-studied problem. I don't expect you to understand what's on this slide, or, I mean, feel free to close your eyes if it scares you. But the point of this slide is simply that to hammer home the point that this is an interesting problem sort of across the spectrum, right? So here, this sort of number line is meant to represent the approximation factor gamma. And you can see that sort of all over the place for gamma equals square root n and n to the 1.5 and 2 to the order n. This is an interesting problem. And lots of work has been done. Of course, this is a small subset of the absurd amount of work that's been done on this problem. It turns out to be important. There are other lattice problems as well. This is, again, meant to be a slide that you're not meant to read. But there are a lot of variants of lattice problems. But it's sort of someone walks up to you on the street and says, like, you know, what do you know about the closest vector problem or the bounded distance decoding problem or something like that? A good rule of thumb is that actually all these problems are effectively the same. So this is a very complicated diagram showing that there are sort of reductions between a million different lattice problems. So I'm only going to talk about SVP, but it turns out that our algorithms for SVP essentially work for all other lattice problems as well. So again, if you're accosted on the street and asked to say what you know about your favorite lattice someone's favorite lattice problem, feel free to pretend that it's SVP. So with that, let me show you some algorithms. So I'm going to start out by showing you approximation algorithms for SVP, and then I'm going to show you some exact algorithms, maybe kind of backwards. So the first algorithm that I'm going to show you is a really, really beautiful algorithm due to Lenstra and Lovash. It's known as the LLL algorithm from 1982. And it's really, really beautiful. It's also not at all obvious why it's useful, as I hope you'll see. I know probably a lot of you have already seen the LLL algorithm, but I don't feel bad about presenting it again because it's just so beautiful and there are different ways to present it, and yeah, it's great. So the LLL algorithm, as I see it, and again, there are different ways to present it, starts out by thinking about SVP in 2 dimensions. So in 2 dimensions, the input to an SVP problem is just B1, B2. So maybe this is B1 and this is B2. So notice that my vectors are column vectors. That's important. If you don't realize that, then you'll get confused. And of course, they're column vectors because I'm civilized. So the idea behind the algorithm I'm going to show you is, so we have B1 and B2, and I'm going to keep modifying B1 and B2 in order to try to satisfy the following 2 conditions. There are 2 very simple conditions. The first condition is that B1 should be shorter than B2. The second condition is that if I add or subtract B1 from B2, it should get longer. In other words, there shouldn't be a trivial way to make B2 shorter, right? I can always add B1 to B2 and I'll stay in the lattice, or subtract. So it seems natural that we should want B2 to satisfy this very basic property that it shouldn't get longer if we just add B1 to it. It turns out that if your basis satisfies these 2 properties, then B1 is in fact the shortest non-zero vector of your lattice. That's actually not entirely trivial. to prove. I'll prove a slightly weaker result, I think, on the next slide. But so let's see how we can imagine sort of enforcing these two conditions. So here's my basis. I've just sort of written it as a matrix now. So remember, my B1 is the first column, my B2 is the second column. And now we can like look at our two conditions, and we can see that like condition 1 is not satisfied. B1 is in fact longer than B2, quite a bit longer, I guess. So there's a natural solution to that, which is I can swap them. So the first thing that my algorithm is going to do when it sees this particular input is it's going to swap B1 and B2. Pretty straightforward, I think. The next thing that we're going to do is slightly more sophisticated. We're going to size reduce. So here we're going to try to enforce condition number 2. So you can see on the, I don't know if you guys can see this pointer. I hope you can. But you can see that in the second matrix, yeah, okay, you can see the pointer. This is useful. So in the second matrix, you can see that I can clearly subtract off B1 from B2, and that vector will get shorter. So size reduction, I take the largest multiple of, could be negative, the largest multiple of B1 and subtract it off from B2, so that's no longer the case. So now this is called size reduction. I don't really know why. I guess it's as good a name as any. And then we're just going to keep going. So now if you look at this basis, well, B1 is longer than B2. So I'm not going to bore you by finishing the whole thing. But if you stare at this for a second, you'll see that after 2 more steps, we actually get to the identity matrix. So it turns out that B1 and B2 actually generate the integer lattice, Z squared, which is not immediately obvious if you look at these basis vectors unless you played with this stuff before. And notice like this algorithm, you know, it's not very sophisticated. It's very simple. It's essentially the Euclidean algorithm. And I think, so I tried to choose the top row of these matrices. I think I succeeded, so that actually we're literally just doing the Euclidean algorithm on the top row in this particular case. But more generally, it's effectively the Euclidean algorithm. And it is a very simple algorithm, and it goes back quite a long way, either to Gauss or Lagrange. I thought it went back to Gauss, but recently Daniele Machancho and Fang Nguyen told me that it might go back to Lagrange. So one of them, neither of them knows the credit. Neither of them needs the credit, rather. Okay, so the LLL algorithm, oh, right. So in order to understand the LLL algorithm, I want to think more deeply about this very, very simple algorithm. So I want to sort of unpack it a little bit. So the way that we're going to unpack it is we're going to define the Gram-Schmidt vector, which I write as B2 tilde. And the Gram-Schmidt vector, well, it's the unique B2 tilde such that I can write B2 as some constant times B1 plus B2 tilde, and B2 tilde is orthogonal to B1. In other words, it's the projection of B2 orthogonal to B1. So this is easy, most easily shown in pictures. So here is my B1. My B2 has some component in the B1 direction and some component out of the B1 direction, and B2 tilde is the component out of the B1 direction. Ugh, tongue twister. So these are called the Gram-Schmidt vectors. I guess because of the Gram-Schmidt process, which you might have learned when you took linear algebra. It's also sometimes known by the QR decomposition, which is sort of a fancier name for the same thing. But anyway, I call them Gram-Schmidt vectors, and they're quite important, actually. Here we're just in 2 dimensions, so they're rather simple. So now let's rewrite our conditions 1 and 2 in terms of this new notation, where I have B2 tilde, mu, and B1. So what I can do is I can write condition 1. It's easier to work with squared norms than norms. And then I can just write the norm of B2 squared as the norm of B2 in the B1 direction, which is mu squared times B1 squared, plus the norm of B2 in the orthogonal direction, which is norm B2 squared. All right, so this is, I guess, the Pythagorean theorem. So the condition that the norm of B1 should be less than the norm of B2 is equivalent to the condition that the squared norm of B1 is less than this sum here. And the condition that B2 cannot be made shorter by adding B1 to it is exactly the same as saying that this mu, which sort of encodes the the B1 coordinate of the B2 vector, this mu should be less than 1/2 in absolute value, right? If it's larger than 1/2, then I can subtract B1, and I'll get a mu smaller than B1/2, and this length over here will go down. Okay, so we can write sort of basic geometric quantities of the lattice in terms of these Gram-Schmidt vectors, in particular the determinant of the lattice. I've not told you what that is, but it's a lattice invariant. You might notice that all of the procedures that I did on this matrix don't change the absolute value of the determinant of the basis. And that's what the determinant of the lattice is. And that's given by the product of B1 times B2 tilde. In other words, the area of the parallelogram spanned by B1 and B2 is the same as the area of the rectangle spanned by B1 and B2 tilde. So that means that actually this is a constant. So no matter what I do to my basis, as long as I keep a basis, this determinant will remain unchanged. So this product will remain unchanged. In addition, we can bound lambda1 in terms of B1 and B2 tilde. So the easy bound is that lambda1 can't be larger than B1, the norm of B1, right? Because if it were larger than the norm of B1, then like B1 would be a shorter vector, and lambda1 is by definition the shortest vector in the lattice, or the length of a shortest vector in the lattice. The less trivial thing to prove is that actually lambda1 is at least either B1 or B2 tilde. So the way that you prove this is like by very simple case analysis. So you first imagine that you take a shortest vector, and you first imagine that it has a non-zero component in the B2 tilde direction. If it has a non-zero component in the B2 tilde direction, because it has integer coordinates in our basis, that means it has to stick out by at least norm B2. So that coordinate has to be at least 1 in absolute value. On the other hand, if it doesn't have a coordinate in the B2 direction, then in the B2 tilde direction, then the shortest vector is in fact B1. So from that we get that lambda1 is bounded between these two values. And I think both of these things suggest that if you want sort of to a nice basis, what you should try to do is make B2 tilde larger and make B1 smaller. Notice that that's actually equivalent because the product is constant. So anyway, let's prove that our algorithm isn't so bad. Let's prove that the norm of B1 is at most square root 4/3 times lambda1 of the lattice. So how do we prove that? Well, notice that this condition, these two conditions combined, imply that the norm of B1 is at most root 4/3 times norm of B2 tilde. That just happens by plugging in a half here and rearranging. And then from our inequality over here, we immediately get the norm of B1 is at most root 4/3 lambda1. So it turns out this is like a sort of quirk of 2 dimensions that actually you can prove via a little bit fancier case analysis that the norm B1 is at most lambda1. It's exactly lambda1, I guess. But if you satisfy these two conditions, you'll at least get an approximate solution to SVP, which is already by itself quite cool. So now let's sort of move up to the LLL algorithm. So the LLL algorithm, we have to generalize this B2 tilde that I had before. Now we're going to have BI tilde, which is just BI projected orthogonally to B1 through BI minus 1. So I take each basis vector and I project it orthogonally to the previous ones. Again, this is like the Gram-Schmidt orthogonalization or the QR decomposition, whatever you want to call it. And it helps, in fact, the QR decomposition does this for you, I guess. It helps to change coordinates that your matrix is upper triangular, right? So I can just like do a change of basis in space, so that my x-axis is B1 tilde in the direction of B1 tilde, my y-axis is in the direction of B2 tilde, my z-axis is in the direction of B3 tilde, etc. I ran out of letters. And then that means that my basis will be upper triangular. And this is a nice way to think about these things. And then like my basis is uniquely determined by these norms, these Gram-Schmidt norms along the diagonal, together with these mu ij's, which are sort of the component of the jth vector in the ith direction. I think I got that right. So So we now have a generalization of that, which follows the exact same proof, which is that in sort of an n-dimensional basis, the shortest vector has length at least the minimal Gram-Schmidt. And the proof is exactly the same, right? So like I say, well, if I have a non-zero nth coordinate, then I have to have length at least norm bn tilde. If not, then if I have a non-zero n minus first coordinate, I have to have length at least bn minus 1 tilde. More generally, sort of your last non-zero coordinate gives you bound on your length. And we also have the property, the determinant of the lattice, which is an invariant, is the product of the Gram-Schmidt vectors. So no matter what we do to our basis, that product's not going to change. Here's the central idea behind the LL algorithm. It's the Lovász condition. So Lovász condition says, well, it's actually exactly the same as the conditions I had a couple slides ago for a two-dimensional lattice, except now you just apply it to Gram-Schmidt vectors in some larger lattice. So in particular, this is saying that the norm of bi tilde is at most, well, the norm of bi plus 1 in sort of the direction of either bi or bi plus 1. So in other words, you look at the lattice generated by bi and bi plus 1, but projected orthogonally to all the I minus 1 guys before, and you want bi tilde to be the shortest vector in that lattice. That's what this is saying, these two things together. So in other words, you look at a little block of the matrix like this, and inside this little block, you should have a solution to SVP. You should have a reduced basis in the sense of Gauss and Lagrange. So it's sort of a very nice, like, little local condition on your basis. This is just me saying it a million times. The goal is to make sure that the first vector in each of these little 2x2 blocks is as short as possible. So not necessarily as short as possible in terms of the whole basis, that would be too hard, but just in terms of what's going on in this 2x2 block. And notice that by the exact same analysis, well, just by algebra, I guess, we see that this means that bi tilde is at most square root 4/3 times bi tilde plus 1, bi plus 1 tilde. The way that we typically say this is that the Gram-Schmidt vectors don't decay too rapidly. And this is really nice because, well, remember that the norm of B1 is at most the minimal norm of any of the Gram-Schmidt vectors. And if we just sort of iterate this inequality over and over and over again, we see that B1 has length at most 4/3 to the n over 2 times norm of bi tilde. And since this quantity, if you minimize over all I, bounds lambda 1, you then get that norm of B1 is at most 4/3 n over 2 lambda 1. It's not obvious at all that that should be useful, right? I mean, if you like first see SVP for the first time, you might not realize that an exponential approximation factor is useful for anything. It turns out to be very useful. Like it can be used to break crypto. Just for completeness, I'll mention that there's actually this factor delta here that you need to put in to make the algorithm terminate. I'm going to show you the algorithm on the next slide, but we don't typically work with exactly this condition. We work with this condition with an extra delta where delta is slightly less than 1. But that's like a minor technical issue. So here's the full algorithm. You just sort of remember these two conditions, and you just sort of iteratively fix these two conditions. So you iterate through all the mu ij, in other words, all the components of the jth vectors in the ith direction. And if any of them have a large component in the ith direction, you just subtract off bi so that it no longer has that large component. So in other words, if 2 is not satisfied, you just fix it. And if 1 is not satisfied, so in other words, if bi tilde is not the shortest vector in the lattice spanned by bi tilde and like bi plus 1 tilde-ish, then you just swap them. You swap the rows bi and bi, the columns I and I plus 1. And then you just do this over and over and over again. So that's the full algorithm. Very, very natural, very simple. It's one of the few ideas that we have in the study of lattice algorithms. Of course, I haven't shown you that this algorithm actually terminates. I showed you that if it does terminate, then it will terminate with a basis that has this property that the norm of B1 is within an exponential factor of lambda 1. The reason that this terminates is because you can show that you can show a potential function, a rather simple potential function that shows that at every step, the potential function goes down and it can't go down forever. And you can maybe kind of imagine what the potential function will be, if you're following at least. It'll be just sort of some kind of function that looks at the length of the Gram-Schmitz and puts more weight on the earlier Gram-Schmitz. And somehow what this algorithm is doing is it's pushing the shorter Gram-Schmitz up to the front of the basis. So what we've learned is that 4/3 to the n/2 SVP can be solved in polynomial time. And I'm not going to go into this, but it turns out that this is extraordinarily useful. It can be used to break crypto. It can be used for all sorts of things, finding integer relations between, or near integer relations even between algebraic constants, all sorts of fun stuff. Let me tell you now about a slightly more sophisticated algorithm, which is known as BKZ. So the BKZ algorithm was originally developed by Schnorr. Remember that the LL algorithm asks you to make sure that the first vector is as short as possible in every 2x2 block. And Schnorr, 5 years later, or thereabouts, asked a very simple question. What happens if instead of 2x2 blocks, we consider k/k blocks? This leads to what's known as the BKZ algorithm for block Korkin-Zolotarev. The idea is to look at these k/k blocks along the diagonal of your upper triangular basis. And you try to enforce the condition that the first vector in each block is as short as possible. Again, not relative to the whole lattice, just relative to this little k/k block. So in other words, you want this to be a solution to SVP in this mini square matrix over here. And the algorithm is, well, it's the same thing. It's like, let's try to enforce this condition over and over and over again. It's actually an algorithm that works with an SVP oracle in k dimensions. So what it will do is it'll look at each k/k block. It will solve SVP in the k/k block. If it finds a vector that's shorter than bi tilde, then it puts that vector where bi tilde was, and then it just keeps going. And there's a little bookkeeping you need to do to make sure that you have numerical stability and stuff, but this is the rough idea. It turns out, so what this gives you is a reduction from approximate SVP in n dimensions to exact SVP in k dimensions, right? So remember that the LL algorithm, really what it was doing is solving SVP in these little 2x2 blocks. And that gave you a solution, exact SVP in 2x2 blocks, and that gave you a solution to approximate SVP in much larger dimensions, in arbitrarily large dimensions. And this is the same thing, except now we don't just reduce to dimension 2, we reduce to dimension k. Unfortunately, this algorithm, as I described it, is not known to terminate in polynomial time. In practice, it does. It works very well. So there's tons of interesting work trying to instantiate this idea. And I'm just going to sort of very briefly mention 2 of them. They're really quite beautiful. So one is the slide reduction technique due to Gamma and Nguyen. Their idea is to only consider very special blocks of the lattice, of the basis. So the blocks that they consider are grouped into 2 categories. They have primal blocks, which are I've circled in blue, and dual blocks, which are circled in like dotted red lines. What the algorithm does is it solves SVP in the blue blocks. So in each blue block, this little shaded blue vector should be as short as possible relative to the k vectors in its block. And in the red blocks, it tries to make this vector actually as long as possible. The last vector in the block as long as possible. And remember that because the product of all the vectors is constant, it's determinant, making the last block longer is kind of like making the first block shorter. And in fact, this is a strict generalization of LLL, because when k equals 2, when these blocks have size 2 by 2, then making the first vector shorter is exactly the same as making the last vector longer, because again, the product of the two is fixed. So this is a very, very elegant idea. I left in this slide a proof of the fact that it works. It requires slightly too much background knowledge for me to prove it, but I left it in anyway just because of the fact that I want you to know that it's a one-slide proof. So it's a very, very elegant algorithm, really, really beautiful. And what it ends up giving you is k to the n over k SVP, a solution to k to the n over k SVP in n dimensions, given an SVP oracle in k dimensions for k less than or equal to n over 2. So this is kind of a complicated expression. It helps to sort of plug in different values for k and see what you get. So for example, if you plug in k equals linear in n, some constant times n, then you'll get a polynomial approximation factor. So that's what's relevant for crypto. So for crypto, we only need to solve approximate SVP, not exact SVP. But the only way we know how to solve approximate SVP is via this reduction. And this reduction only saves us a constant in the dimension. You can also plug in k equals log n. This turns out to be the parameter at which this gives a polynomial time reduction. And then you get something a little better than 2 to the n. You can also plug in like k some large constant, and you'll see you'll get an exponential approximation factor that's a bit better than LLL. So maybe the most important thing from this is that you can actually beat, well, I don't know if it's a supporting thing, but one thing from this is that you can actually beat LLL slightly. You can save some polylogs in the exponent by taking k to be logarithmic. But I think I'll not say more about that. And I'll just mention there are other ideas as well. So Machancho and Walter have this really beautiful algorithm called dual BKZ, and it's sort of like the mother of all BKZ algorithms. It just reduces everything. So sort of every block is SVP reduced and dual reduced. This turns out to work. It only solves a slight variant of SVP, but it's good enough. But the high order bit here is that we know a non-trivial reduction from approximate lattice problems to exact SVP. So there's a trivial algorithm, there's a trivial reduction, obviously. I can reduce n-dimensional approximate SVP to n-dimensional exact SVP. What's non-trivial here is that I can lower the dimension. So that's sort of my spiel about approximate lattice algorithms. Now might be a good time for questions. I don't know if we can really stop to take them, but otherwise I'll move on to exact and near exact SVP. Okay, I guess I'll move on. So now we're solving exact SVP. We're looking for exact shortest vectors in a lattice. A lot of the algorithms that we use for this are known as sieving algorithms. This idea was originated by Aitai Kumar and Shiva Kumar. This is Kumar's picture on his website. I don't know why. And their algorithm was the first exponential time algorithm for SVP. And still our fastest algorithms for this problem happen to run in 2 to the order n time. And you'll kind of see why. I hope you'll see why in a couple of slides. So let me tell you how their algorithm works, how sieving works in general. So remember that when we're given as input a lattice, what that really means is we're given as input some lattice vectors. There are typically, there will be n of them, right? They'll be the basis vectors. So here n is 2, so I put 2 vectors here. So you're given sort of 2 points in space. And the first step in a sieving algorithm is to get a lot more points. So you generate a ton more lattice points that all have roughly the same length of the points that you started with. So the way that you can do this is by taking, say, random plus minus combinations of your basis vectors. So that'll give you 2 to the n points, for example. We have more clever ways to do it, but that's good enough, I think. And the idea here is that if I have enough points in space that are all roughly the same length, they all have bounded length, then eventually I'm going to find a pair of them that's close together. Space gets crowded eventually. So here I have a pair of lattice vectors that are close together. And of course, the lattice is closed under taking differences. So I can take the difference of these 2 lattice vectors, and it'll give me this purple vector over here. And because these 2 vectors were close together, well, their difference is short. So I've taken my 2 close vectors and converted them into 1 short vector. And sieving doesn't just do this once, it does it like many, many times. So you find many, many pairs of short vectors. In fact, you'll start out with exponentially many vectors, and you want to end up with roughly the same number of vectors that you started with. So you find as many pairs as there are vectors that you started with. And this works great. You get all these purple vectors. There is a minor issue that comes up, which might seem kind of trivial, which is that occasionally this happens, right? So I already have this purple vector over here in my set of purple vectors, and take the difference of these 2 vectors, and I find the same vector again, which is kind of funny. So what are we going to do? Maybe we'll take it twice, or we won't take it. Either way, it's going to be a problem. I'll explain that more on the next slide. But anyway, the next step in the sieving algorithm, notice that none of these is the shortest vector in my lattice. The next step in the algorithm is to forget about all the red vectors and then do the same thing on the purple vectors, right? If we got enough purple vectors, then space is going to get a little crowded. We're going to find pairs of them that are close together. So here's a pair that's very close together. I sort of rigged it so that this stops in 2 steps. In practice, it stops in many more. But anyway, if you keep going for long enough and you choose your parameters properly, you'll find a shortest vector. And this is sort of an algorithmic framework, and there are lots of design decisions, sort of modular things that you can change in this algorithm. So like one question is, what do you start with? In other words, how do you sample the original vectors? The next question is like, how do you find close pairs of vectors? You could iterate through all possible pairs, but that seems a little wasteful. Can you do better? And finally, like what do you declare as a close pair? Like how do you decide when to take a difference and when not to take a difference? And like changing all of these leads to different algorithms. So this is a beautiful algorithm, I think, a really beautiful, simple idea. It's an extremely natural technique, right? You want to find a short vector in a lattice. So what do? You start out with a bunch of long vectors and you try to make sort of local changes to make your vectors shorter and shorter and shorter. So you just subtract pairs. And sort of the best thing about this algorithm is that it can be made to work. But the way that I showed it to you, well, maybe I didn't show you a complete algorithm, but there's a lot more that you have to do to actually make this work provably. And the reason for this is really silly. It's that this algorithm is very hard to analyze because no matter what distribution we start out with at the beginning of this procedure, it's very difficult to say what distribution. So our vectors are going to be random at the beginning, say uniformly random in a ball. But then in the next step, our vectors are going to be like uniformly random from pairs of vectors that were close together in the previous step or something like this. Differences of pairs of vectors in the previous step or something like this. It gets really ugly. And then we're going to do that like polynomially many times. So it's a huge mess. And the only thing we want to know about this algorithm is how common collisions are. Because if I get a collision and I take the same vector twice, that means in the next step, I'm going to subtract a vector from itself and I'm going to get 0, which is not good, right? So we want a shortest non-zero vector. And the problem is maybe the algorithm is sort of too clever by half and finds 0 over and over and over again. So in order to analyze this algorithm, you have to somehow prove that it doesn't sort of, by coincidence, find the same vector over and over and over again, because that will give you zeros. And proving that little one extra step is all you need, because the algorithm by design gets shorter and shorter vectors at each step. So eventually they're going to have length lambda1. They're going to have the length that you want, or bounded by what you want. You just want to make sure that they're non-zero. So there are many solutions to this problem of figuring out what the distribution is at each step. The simplest solution, which is actually very clever, is to assume that the vectors are distributed nicely. So assume that they're like uniformly random on a sphere or something like this. And this is the heuristic solution, and it gives the fastest algorithms. Maybe that's not surprising. So if you assume that the algorithm performs well, then the algorithm will perform quite well. So these are the fastest algorithms that we know, and these are the algorithms that are relevant to crypto, because if your adversary is trying to break a cryptographic scheme, he doesn't have to prove that his algorithm works, he just has to hand you your secret key. That's good enough, right? And in practice, these algorithms work. And what's nice is that, like, once you have the freedom to assume that the vectors are distributed nicely, you can do lots of other things. Like you can use fast near neighbor search algorithms to really optimize the running time of these things. The other solution, which was AKS's original, is actually really quite silly. It's you add noise to your vectors so that collisions are unlikely. So what you do is you, instead of showing your algorithm, which is going to take these pairs and subtract them, your actual vectors, you show them your vectors plus some noise. And then you prove that your algorithm can't have found zero because, or can't have found zero more than it found a shortest vector, because from its perspective, they look essentially the same. So you treat your algorithm as an adversary. It's a very strange thing. I don't know another example of this. But that's still the state of the art for this kind of algorithm. Another approach that we started in 2015 with Devesh Agrawal, Daniel Dadouche, and Oded Regev was, instead of taking differences of close vectors, to do what I'm now calling sieving by averages. And I'll now sort of show you that. Here's a table showing you all the running times of all these different things. It's tremendously complicated, but the rough idea is that heuristic algorithms give you quite fast running time. They're all exponential, but the constant differs quite a bit. So heuristic algorithms give you 2 to the 0.29n, which is 3/2 to the n over 2. It's like a fundamental geometric constant. Our fastest provable algorithm runs in 2 to the n time, and I'll kind of show you that in the next couple of slides. And if you use this perturbation method, you can get a little below 2 to the n, but you only solve approximate SVP for like a constant approximation factor as it happens. And we think we can get down to 2 to the n over 2, but we're not quite there yet. So that's the current state of the art. I don't expect you to remember much of this if you're not an expert. The point is that it's actually rather complicated. So let me show you the sieving by averages algorithm. The idea starts out by saying, suppose instead of taking differences of lattice vectors, what if I take averages? So instead of doing x minus y, I do x plus y over 2. Why not? Well, here's why not. If I give you x, y in the lattice and I take their average, so here's the average, typically the average will not be in the lattice, right? Lattices are closed under taking differences. That's why sieving makes sense. Lattices are not closed under taking averages. But it turns out that this is a good idea. And it turns out it's worth pursuing. So let's try to force it through. Let's ask, well, when is the average of 2 lattice vectors in the lattice? And we have to remember what it means to be a lattice vector. It means that I can write you with integer coordinates in terms of my basis, b1 through bn. So here these aij's are all integers. And then, you know, the average is a linear operation. So the average of the coordinates of the average are the averages of the coordinates. I think I said that right. And then these are going to be integers if and only if these two coordinates have the same parity, right? So if each of these pairs of coordinates have the same parity, so if they're all equal mod 2, then the average of these two vectors will be a lattice vector. The fancy algebraic way to say this is that the average of 2 vectors is in the lattice if and only if they're equivalent modulo twice the lattice. So in other words, just to say it again, y1 and y2 have their average in the lattice if they lie in the same coset modulo twice the lattice. And notice that there are 2 to the n cosets. There's one coset for every possible vector of parities of these aij's, right? So for every possible binary vector in n dimensions. So our sieving by averages algorithm works as follows. You start out with randomly sampled vectors. The distribution actually really matters. It's called the discrete Gaussian. I wrote my whole thesis on it, but for now, we'll just sweep that under the rug. You start out with some random vectors chosen cleverly, but you don't look at all vectors at once. Instead, you just look at all the vectors that lie in a coset. So all of these vectors happen to lie in the same coset modulo 2L. Let me prove that to you. I can just show you that if I take their pairs and take their averages, well, each of their averages is the lattice vector, which means they lie in the same coset. We just showed that. So that's what your algorithm does. It pairs them up and takes their averages and gets some purple vectors. Then it looks at the next coset of red vectors, pairs them up, gets some purple vectors, and keeps going. So the full algorithm works as follows. You start with many samples. Vectors sample from a nice distribution over your lattice. You iterate through the cosets and group vectors into disjoint pairs. You do so randomly. You don't like look at their lengths and try to find pairs that have a small average or anything like that. You just do so randomly. And then you take the average of each pair. And you repeat this procedure on the averages. That's the whole algorithm. This is our fastest algorithm for SVP. We call it an embarrassingly simple algorithm because it's embarrassingly simple. And the intuition for why this should work is, well, if you have 2 random vectors and you take their average, you expect their length to go down by like square root 2, right? If I take 2 Gaussian vectors and I add them together and divide by 2, the length will go down by a factor square root 2. That's like the fact that variance is additive. Furthermore, because this algorithm does sort of a nice algebraic thing of taking the average and never looks at lengths, we can explicitly bound the probability of a collision, which is what we need. So we have sort of the 2 properties that we need for a sieving algorithm to work. The vectors get shorter, at least on the average, and we don't get 0 too much. It turns out that this takes 2 to the n time and space because there are 2 to the n cosets, and we have to iterate through all the cosets. So that's what the running time is governed by. And as I said, this is still the fastest algorithm for SVP with proven correctness. Our original version of it was a little more complicated, but it turns out that this simple algorithm literally works. It's embarrassing. So maybe, how am I doing on time? I can see that something has been going for an hour, but I don't know if it's my talk or since Tomas started talking. So I don't know how much time I have left. Maybe someone can tell me.
No, that's okay. It started with my talk, so you can go on.
Okay. I think I'm pretty close to done. I'll just mention that we think we can get down to 2 to the n over 2. We're really, really close. And the idea here is instead of matching every coordinate, so instead of making sure that the parities of each coordinate of these vectors is the same, we only match about half of them. Then when you take the average of vectors, you won't be in the lattice anymore, but it turns out that's okay. You can fix that. And we already know that this works for approximate decision SVP and a variant called Hermite SVP. This is what this technically means. Don't worry about it. The point is that we think we can improve this. In contrast, these heuristic sieving algorithms, you just pretend that your vectors are always uniformly random on a sphere. And that means that you need 4/3 to the n over 2 vectors to have a chance of finding many close pairs. It turns out that this 4/3 to the n over 2 is exactly the same 4/3 to the n over 2 that arises in the LLL algorithm. But here, it's used as the number of vectors that you need to have on a sphere, random vectors, before you're guaranteed to have a vector close to every point on the sphere. So the fastest algorithms, they're governed by this constant, well, it's not a constant, by this geometric number, this 4/3 to the n over 2. And the fastest algorithm use locality sensitive hashing, so they use very clever tricks. If you work naively with this, these 4/3 to the n over 2 vectors, you get a running time of 4/3 to the n, because they're the number of pairs of vectors amongst these is 4/3 to the n, but via locality sensitive hashing, you can get that down a little bit. And there's tons of work on this, trading off time for space and taking k-tuples instead of pairs and all sorts of clever things. Via the perturbation method, which I mentioned before, where you add noise to your points, for exact SVP, the best we know is still 2 to the 2.5n, so quite a bit slower than, 2 to the 5n, quite a bit slower than what we know. I think this is actually wrong, and the right answer is, in fact, 2 to the 2.5n. Anyway. And for constant factor approximation, we actually know how to do a little better than 2 to the n. We know how to do 2 to the 0.802n. And these are actually fundamental geometric constants as well, or there are best bounds on fundamental geometric constants. I was going to say a little bit about other exact algorithms, but I think I'll skip it. There exist other exact algorithms. They're a little slower. But yeah, I think I'll skip that, and I'll just thank you for your attention.